Hello, and welcome back to a video series on MAC 2311 Calculus 1. My name is Sean Perry. These are guided notes number 4 in the series on properties of limits, Part 1, finite limits. In this video, we're going to talk about limits where either the limit or the number that x approaches is just a finite real number. When learning about any new math, it's important to see how it works, yes, but also how it works with any math that you learned previously. Specifically, we want to see how limits are going to work with function algebra. What is the relationship between the limits of functions and the limits of their sum, difference, product, quotient, and composition? We really want to know if order matters when we take a limit. What we're going to find is that limits are very well behaved when it comes to the order of operations. We've seen similar considerations about order mattering before, for instance with commutativity. This is order around the operation. Does the left or the right side of the operation matter? We know that when summing or taking the product, it doesn't matter what order I write, but we know that for differences and quotients, the order indeed matters. We've also seen this with associativity, that is to say, the order of evaluation. It doesn't matter what order I sum, and that's why often we simply drop the parentheses with sums. Likewise for products, but for differences and quotients, again, it matters where I put the parentheses, and so just writing a long line of subtractions or quotients is not unambiguous the way that writing a sum of many things or a product of many things would be. Many important operations do not have these properties. Exponentiation is neither commutative nor associative. For example, if I take 2 to the third power, that's 8, but 3 to the second is 9. Or if I want to know what is 2 to the 3 to the 2, well, it matters what order we do the exponentiation in. If I took 2 to the power of 3 to the 2, and I did the 3 to the 2 first, that'd be 2 to the 9, or 512. But if I did 2 to the 3 to the 2, and I did the 2 to the 3 first, well, that would be 8 to the 2, and that would be 64. So, in other words, we have to agree beforehand which we're going to do, or just writing a bunch of exponents isn't unambiguous. Another way we can see order mattering in action is to look at the distributive property. Here, I can do a times the sum b plus c by either taking b plus c first, that's the left-hand side, or distributing the a and multiplying it by both the b and the c. Likewise for distribution of exponentiation around products and quotients. I'd just like to point out that this does not occur as distribution of exponents around sums, neither radicals, which are just a kind of fractional exponent around sums, or differences. This is a common mistake. Please don't fall for it. What we see here with the cases of the distributive property is a way of changing the order of operations, really. I could do my producting first if I wanted to, or I could do my summing first. But there's a cost to doing the producting first. I would have to do it to both terms. We will see a pattern very similar to this presently when we look at limits. There are two more examples I would like to include of order mattering to get a sense of what kinds of patterns we're going to be seeing in this class. One is function composition. In general, please recall that if I compose a function with another, the order definitely matters. If you'd like a review on function composition, please check out my intermediate or college algebra series. The other example I want to mention is perhaps less familiar. This is implication. Recall that if I write this collection of symbols A, double arrow, B, what I'm saying here is A implies B, or rather, if A happens, then B must happen. We use this to indicate that B is a property which follows automatically and necessarily from A. If A happens, B must happen too. If A is a property that something has, it implies that B must also be a property that that thing has. But in general, with implication statements, order matters. The statement, if it's raining, then I wear my boots, is quite a bit different from, if I wear my boots, then it's raining, which would make me some kind of rain wizard. That's a silly example, but this is going to show up a lot when we discuss theorems in this class and how to use them. We'll have a set of premises, the if part, and we'll have a set of conclusions. It's very important to keep those straight. We're going to want to know when we study theorems in this class what they say, and also what they don't really say. what we can get from the theorem versus its limitations. Okay, that's the introduction. Now let's talk about the properties of limits. The following is an important list. I would memorize it, yes, but also try to see the pattern that ties all the properties together. To begin, let's presume that we have two limits for these two different functions as they approach the same value c. So let's let the limit of f of x as x approaches c be equal to L, and let's let the limit as x approaches c of g of x be equal to m. We're going to presume here that c, L, and m are just real numbers. We're going to see in the next video what to do if c is infinity or if L or m are infinity. For right now, just think of them as regular old finite numbers. First, let's look at the sum property. If I take the limit of the sum of functions, that turns out to just be the sum of the two limits. Notice that this looks like distributing the limit symbol across both f and g, and that it looks like just replacing these with their limits when we consider what the total limit of the sum of the functions should be. The same pattern holds for differences. The limit of the difference is the difference of the limits. This looks like distributing the limit around the minus sign. Unlike other operators, which have different patterns when we pass from sums to products, here the limit just distributes again. This is what I mean when I say the limit is very well behaved. It just does this same kind of pattern over and over. The limit of a product is the product of the limits. We simply take the limit of each one separately and then multiply them together, as if we distributed the limit around the product. A special case of this that comes up frequently is when we want to quote-unquote pull out constants from a limit. So if g of x was just a constant k, then you could pull that out from the limit and just evaluate the limit at f of x. Sometimes the sum property and this constant product property are referred to together as linearity. We may have an occasion to see that later in the course. The same pattern holds for quotients, as does for products. The limit of a quotient is the quotient of the limits. This, of course, is contingent upon m not being equal to 0, because in that case, this expression on the right-hand side would be undefined. There may be ways that we can make sense of a 0 appearing in this denominator, but this property simply could not be applied to just evaluate in terms of the limits of f of x and g of x themselves. There are many other properties that we could prove about the arithmetic of limits, but for brevity, let's just say a couple more. If I have a positive integer, n, then the limit of f of x to the n is the same as the limit of f of x itself raised to the n, or L to the n. If you covered induction in your pre-calculus class, I'll just mention that you could get this fact from taking f of x equal to g of x, that is to say multiplying f of x by itself, and then induct on how many times you're doing that. Another very powerful property is for logs of limits and limits of logs. If your limit of f of x, that is to say if L is positive, so that taking its logarithm makes simple sense, then we can pass the limit inside of the logarithm. That is to say, the log of the limit is the limit of the log. We'll see later how this relates to e, how this property allows us to do some pretty spectacular tricks in calculus, taking full advantage of the property of logarithms to reduce operators. Finally, we'll do one more property that has to do with composition of functions. For this, we'll need to consider what happens when the limit of g of x as x approaches c is m, but f of x is now going to have a limit of L when x approaches m. That's this m. So we want to consider the composition of two functions, where first I am evaluating the innermost function g of x and taking its limit as x approaches c. If that's m, then I could just as easily consider what happens when x approaches m of f of x, which would give me L. In words, if we take the limit of a composition, then we can take the limit of the inside function, find out its limit, m, and then consider what happens when we take the limit of f of x, notice there is no g of x here now, as x approaches m. Said in words, the limit of a composition is the limit of the outside function as it approaches the limit of the inside function. I think that's complicated enough to merit an example. Let's do a simple one that could be evaluated several different ways. Here I have the limit of the quantity x squared plus 1 raised to the fourth power as x approaches 1. We could see this as a composition, where the outside function f of x is equal to x to the fourth power, and the inside function g of x is equal to x squared plus 1. Now, if we consider just the limit of the inside function, the limit, as x approaches 1, of x squared plus 1 is equal to 2. If we want to consider the limit of the composition, we could just consider the limit as x approaches 2 of f of x. Now, f of x was x to the fourth power alone. So what happens as that approaches 2? Well, to be very picky here, as much as we'd like to just substitute in 2, take it to the fourth power and get 16, we haven't established that property yet. We could get these last equalities from the power rule, the sum rule, and so on, but we're going to need the fact that the limit of x as x approaches c is just c. And while this may be readily apparent, in order to be very rigorous, we're going to want to prove that. Proofs involving limits, in order to be truly rigorous, have to use the delta epsilon version of the definition of a limit, and you might think to yourself, this is a bit overkill. After all, that last one really did seem like we could just substitute in the value in the first place. And while that's certainly true in this example, it is not always true. We're going to learn about situations where the limit might exist, and yet the function value is not defined. We'll discuss this and other ways that it can fail presently, and again more thoroughly in a video on continuity that is to follow. Now we're going to use deltas and epsilons in order to prove a couple of key facts. We didn't prove any of the properties that I've asserted already, and it's quite challenging, but you may want to consider what it would take in order to prove those properties in this way. It's a good idea to challenge yourself by thinking slightly beyond the level where you're at. The two fundamental and perhaps obvious limits that we're going to want to have on deck in order to get started using the properties that we've listed already are these. The limit of a constant function a as x approaches c, or any other number, is just that constant a. And the limit of x as x approaches c is just that constant c. Recall that in order to prove something with deltas and epsilons, we need to consider an arbitrarily small epsilon, and then find a delta where any x, which is that close, delta close to c, will ensure that the limit and the function value are epsilon close to each other. But for this constant function, f of x equals a, whose limit is a, well, the difference of those two values is 0. And so that's less than epsilon for any positive epsilon. Hence, for any delta, any x will do. It doesn't matter what x minus c is. It doesn't matter what delta is. We know that f of x minus L will be less than epsilon, and so we have the convergence that we desired. Likewise, let's consider when the function value is itself x. If I have an epsilon arbitrarily small who's been given, if I just choose delta to be equal to that same epsilon, we have the inequality that we need. If x minus c is less than delta in magnitude, which is to say x is at least that close, delta close, to c, then f of x is at least delta close to L. And that's because f of x is just x in this case, and L is just c. And hey, where have we seen those guys before? Exactly when we talked about the conditions on delta. And delta being equal to epsilon means that if we follow this chain backwards, that the magnitude of f of x minus L is less than epsilon. And that's what we wanted to show to prove the limit is what we claimed it was. So from now on, we'll be able to use that as a fact to get started using our properties of limits. And so for these examples of the composition property, we have here that the limit as x approaches 2 is 16, because we could pull out the fourth power. The limit of x approaching 2 is 2, and then 2 to the fourth power is 16. Likewise here, we're applying the sum and power rules, but we could break this up into a constant function using the sum rule and a quadratic function. The limit as x approaches 1 of the constant 1 is just 1, and then using the power rule, the limit as x approaches 1 of x squared would just be 1 as well. 1 plus 1 is 2, or so I've been told, and so we have this first fact as well. It might seem like overkill, but it's a good idea to keep things rigorous. Let's talk about one of my favorite theorems, the squeeze theorem. What the squeeze theorem essentially does is it takes a middle function, f of x, which could be very, very wiggly, and something that we can't clearly see its limit right off the bat. But if we can trap it between a function above it and a function below it, whose limits we do know, say, for example, this upper function g of x and this lower function h of x both have a limit L at c. Then they squeeze f of x and force it to have the same limit by trapping it between them. Let's look at an example of this theorem in action. Let's say we had f of x equal to x times sine of 1 over x. What is the limit as x approaches 0? Notice this function is not continuous there. In fact, we know from previous examples that sine of 1 over x is going to wiggle very, very much as we approach 0. Moreover, the limit as x approaches 0 of 1 over x doesn't exist, so we couldn't use composition anyway. But we are able to trap this troublesome wiggle in between two values, in between positive 1 and negative 1, because that's as big as sine will ever get. Now, take a moment to think about this next line. If I then multiply sine of 1 over x, which is between 1 and negative 1, by a value x, this could be no bigger than the magnitude of x, because sine could be no bigger than 1, and it could be at its smallest negative the magnitude of x. So these give me two functions which are bounds for the function whose limit we're interested in. And we know their limits. In fact, because we know their limits, and because their limit goes to the same value, 0, we also know the limit of the function that they squeeze. So here's a graph of x times sine over 1 over x. If I zoom in, we can see that this is starting to get very, very wiggly near 0, but we can also see that it's sort of shrinking. It seems to be going off into the distance there as the magnitude gets smaller and smaller. That's because we're multiplying by x here, and x is going towards 0 as sine of 1 over x stays bounded between negative 1 and positive 1. Now let's take a look at these bounding functions. Here is the absolute value of x, and here is the negative absolute value of x. And we notice that these are trapping our pesky wiggly function between them. But not just that, they are also diving down towards the same limit themselves, right? This positive abs val has a limit of 0 as we approach from the left and right, and so does this negative abs val. And yet the blue function x sine of 1 over x is trapped between them always. This is the essence of the squeeze theorem. It says that even though we don't exactly have a great handle on the behavior of x times sine of 1 over x as it goes towards 0, we do know that its magnitude also dives down to 0 and is in fact trapped between these two functions. That's exactly what's going to let us use the squeeze theorem here to say that the limit of our function in blue is also 0 as x approaches 0. Let's look at another application of the squeeze theorem in order to prove what we've already claimed, which is the limit as x approaches 0 of sine of x over x is equal to 1. Note that we're not really allowed to use the quotient property here, as that would put a 0 in the denominator. The proof is a geometric one. Consider this pi slice of the unit circle. That is to say, AC is of length 1, and these are circular arcs here. As you may remember from pre-calculus, the area of this sector is 1/2 theta r squared, where theta is given in radians. R, in this case, for sector ABC, is going to be 1, and so this is just 1/2 theta. The area of the right triangle, whose opposite is in blue here, that is to say triangle ADB, is 1/2 its base times its height. Its base is cosine theta, and its height is sine theta, giving me 1/2 cosine theta sine theta as its area. Finally, we can look at the area of the smaller sector, AED. Remember, that's this guy right here. Now, he doesn't have radius 1 anymore. He has radius cosine theta. So plugging that into the area of a sector, we have 1/2 theta cosine squared of theta. Now, it should be a little obvious from some size comparison here, since the areas are nested, that the area marked A1 in red is less than or equal to the area A2 in blue, is less than or equal to the area A3 Now, those we calculated as follows. So we have this chain of inequalities. What we're going to want to do is manipulate this middle term until it looks like sine theta over theta. And to do that, we need to get rid of cosine. We're allowed to divide by cosine here because it's not going to be equal to 0, because we're going to be close to a value of 0 when we're talking about our limit. Moreover, when we talk about limits, we're going to talk about theta not being equal to 0 because we're just approaching it. That means we can divide by cosine and divide by theta. Let's also divide by that pesky 1/2 as well, and when we do, we get what we're looking for in the middle. We have cosine of theta is less than or equal to sine of theta over theta is less than or equal to 1 over cosine of theta, also known as secant of theta. Now, although I haven't proven it to you numerically yet, it should be available to you from a graph of cosine that the limit of cosine of theta as theta approaches 0 is 1, and likewise for 1 over cosine. If you assume what's in red, what's in green follows from the quotient rule. Now, because the function in blue here was trapped between the function in red and the function in green, and because they have the same limit, it forces the middle term to also have the same limit. It makes no difference whether or not you call this theta or you call this x, and so our theorem is proven. So here I've graphed sine of x over x, 1 over cosine of x, which, as you know, is secant, and cosine of x, which is in red here. Let's zoom in to the point in question. We were asking about what happens as we approach 0. And we notice that our secant, our cosine, and the function we're looking to bound, sine of x over x, are in the correct arrangement to do the squeeze theorem. We have a function above, a function below, a weird function that we've trapped in between them, and they're all diving in towards the same limit as we approach from the left and the right. Here are some other formula that you might find interesting or perhaps useful in the future that share some similarities with the limit of sine of x over x. Notice that the limit of tangent of x over x as x approaches 0 is also 1. The limit of 1 minus cosine of x all over x as x approaches 0 is 0. And the limit as x approaches 0 of 1 plus x to the power of 1 over x is going to be equal to e in the limit. This last one you should be a little bit wary about, since the limit of 1 over x as x approaches 0 is undefined. As we approach from the right, we get positive infinity. As we approach from the left, we get negative infinity. And this argument inside here will either be a very small increase from 1 or a very small decrease from 1, respectively. However, looking at the graph, we get some pretty convincing evidence that actually this is converging towards a single number. And what we'll find is that number is going to be precisely the constant e. You've probably seen e before in the context of compound interest, continuously compounded interest. But in this class, we're going to see that e is actually quite a bit more fundamental than that. No spoilers, but we're going to find out in this class why we would call log base e the natural logarithm. Let's return briefly to the question of, are limits really just plugging things in? What we've seen with the last few examples is certainly not, because just plugging things in would give us undefined expressions. The limit of a function is sometimes, but not always, equal to its evaluation. That condition where it is equal to its evaluation, that is to say the limit as x approaches c, is the same thing you get when you just plug in c. This is a condition called being continuous at c. It implicitly assumes that f of c is defined, that the limit of f of x as x approaches c exists, and that these two are equal to each other. And because those three presumptions are happening in the background, this expression might fail if any of these don't happen. That is to say, if the limit and the evaluation aren't equal. We've seen some examples of that with piecewise functions. If the limit doesn't exist, which might happen even if the function value does, and if the function value doesn't exist. For example, what if c is outside of the domain of f? Maybe you would divide by 0 there. If that happens, the function is not continuous at that point, and its limit does not equal its evaluation. We're going to go into more detail about continuity, this property of being continuous, in a couple videos. For now, you can take for granted that all polynomials, including the identity function x, rational functions, exponents, logs, radicals, trig functions, all of these are continuous. They have the property at every c in their domain. You should be on guard that piecewise functions and points outside the domain or right on the edge of domains frequently lack this property of continuity. So that gives us a lot of limits that we can really take just by plugging in. Let's do one more thing to sort of shore up when we can and can't plug in and leave the rest for the continuity video. We've seen that certain times cancellation will allow us to consider a simpler function even if we are undefined at a single point. For example, the function x over x is equal to 1 everywhere except for x equals 0, where it's undefined. And because it's equal to 1 everywhere, that means the limit as we approach 0 would be equal to 1, even though the discontinuity is happening at the point 0. So let's generalize this observation into a theorem. We'll call it the point discontinuity theorem. And it says that if we have two functions, f of x and g of x, and they are equal to each other, except perhaps at one single point, the point we're approaching, c, then if we know that one of those functions has a limit of L as x approaches c, then so must the other. For example, in this last one, the constant function 1 is playing the role of g of x. X over x is equal to 1 everywhere, except for at 0. So that means instead of looking at x over x, I'm free to look at 1, a pretty simple function, when taking the limit. That's what this lets us do. If we know that we're only not equal to something at a single point that we are approaching as a limit, we can take a look at the simpler function instead. You'll see some examples of this as you do your homework. But for now, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.